This video gives an introduction to isomorphisms and isomorphic graphs. So to start off with, I want to look at an example before we get into any of the terminologies. So we have two graphs here, graph G and H. Both of them have 4 vertices and 6 edges. And the question here is, are these two graphs, barring the changes in labels on the vertices, are these two pictures of these two graphs really representing the same underlying graphical structure? In other words, if we erased those labels on the vertices of H and changed the 1, 2, 3, and 4 to A, B, C, and D, would we actually have the exact same graph if we wrote it out as their vertex and edge sets? Well, in order to do that, let's actually just try to redraw the graph G, where the vertices are in the exact same orientation as in our graph H. If we can redraw the vertices A through D in the same orientation as graph H, and then all of the edges in graph G as they move when the vertices move, if the resulting new picture is exactly the same as the picture for graph H, that would mean the answer is yes, these two graphs represent the same information. Okay? So, for this guy here, let's first go ahead and, well, I'll be slightly lazy. I'm not going to change the orientation of where vertex D and vertex C live. So that would mean that the edge between vertex C and vertex D would still be that horizontally oriented edge. Now what I will do is I'll focus here on vertex B, and I'm going to move vertex B down a little bit. So I'll move vertex B down to here, except I should write a B. Now vertex B is adjacent to vertex C, D, and A. A isn't drawn in yet, but I can go ahead and connect the edges B to D and B to C. Okay. Now, we do still have vertex A, so I'm going to go ahead and put vertex A up here at the top. If we look at vertex A, we see that vertex A is adjacent to B. Vertex A is adjacent to C. Vertex A is also adjacent to B. And now we do a quick double check to make sure that we have all of the edges. Vertex A was adjacent to everybody else. We just drew that in. Vertex B adjacent to all the other vertices. Got that. Vertex C adjacent to all the other vertices, and same deal with D. So this here is simply taking graph G, redrawing it, and you put the actual vertices in a different orientation. Now we do a comparison between this graph that we just got, this new picture of our graph G that we just got, in the original graph H. And notice what we can do. If we look at these two graphs, so I've labeled the columns here graph G and graph H. If we look at the vertices in graph G, A, B, C, and D, we can see that there is a exact one-to-one correspondence between the vertices of graph G and the vertices of graph H. Specifically here, we can say that that vertex labeled 1 in H corresponds to the vertex labeled A in graph G. We can see here that B, we put it in the center when we reoriented our vertices from graph G. That corresponds now to vertex 3 in graph H. Down here, we see that that corresponds to vertex C in the redrawn graph G. And lastly, we see that the vertex D corresponds to vertex 4 over in graph H. Once you have this one-to-one correspondence, in other words, you were able to redraw one of the graphs so it looks identical to the other graph, this tells you that the underlying structure of the two graphs is literally identical. The only change here was the fact that we relabeled the vertices on H. Now this is an extremely important thing that we use in graph theory all the time, and the special name that we call these types of graphs are, these two types of graphs are called isomorphic graphs. And isomorphic just means they have the same underlying structure, but you might have drawn them where the vertices are in a different orientation. Now, there's 2 words actually that go with isomorphic graphs. One is that buzzword of isomorphic graphs, and the other one is something called an isomorphism. In math, if you ever see a word and it ends with this ending that's an ism right here, that actually tells you that you're dealing with a function. So an isomorphism is that actual one-to-one correspondence. This is that correspondence that we have right here where we said which vertices correspond to which vertices across the two graphs. So an isomorphism is that actual mapping. Okay? And what this does is, in order to be an isomorphism and not just a random mapping where you take all the vertices from one graph and assign them to all the vertices in the other graph, there's no guarantee that it would actually work. The thing that makes it work says, all right, you've assigned vertices from the first graph to vertices from the second graph. If you end up with two vertices that are the endpoint of an edge in the first graph, when you then look at those corresponding two vertices in the second graph, you also have to have a corresponding edge. If you have that criteria, then your function is called an isomorphism. Okay? So it's got to be a one-to-one mapping, and you have the correspondence where an edge in the first graph gets mapped fully to an edge in the second graph. Now, if you have this isomorphism existing between your two graphs, that's when you'll get that the two graphs are isomorphic. In other words, they structurally are the same. And if you want to think about this in terms of layman's terms, this is where you redraw the picture and you swap out the labels if you needed to. Okay? And that's it. That's all there is to isomorphic graphs and isomorphisms. Now, determining if two graphs are isomorphic or finding the isomorphism, that can take a little bit of work, but the underlying theory of what's going on, that's all you need to know. Okay? Now, let us look at an example. So here's another example. This example here, we have what? We have 6 vertices for both of these two graphs. So let's go ahead and write that out. So for graph G, the number of vertices is 6. And if we look at the number of edges here in graph G, we have 1, 2, 3, 4, 5 edges. Okay? Now, if we look at our second graph, graph H, we see we also have 6 vertices. So far looking good. We don't have labels on either of these two graphs, but we could totally put labels on and then see if we can find a one-to-one mapping or an isomorphism between these two graphs. But before we do that, let's go ahead and count up the number of edges in this second graph H right here. And in H, when we count up the edges, we have 1, 2, 3, 4, 5, 6 edges. And this is where you should say, hold up, wait a second, we have a problem. Okay. In this particular case, notice these two graphs, while they do have exactly the same number of vertices, they don't have the same number of edges. So what that tells you is structurally they're different, meaning it's not just the same graph that's redrawn, because you actually have an extra edge in that second graph. And in fact, you have more than just an extra edge in that second graph. You've got right here a little length 3 cycle in that second graph H, and there's no cycle whatsoever in your first graph G. So notice that tells you a second thing of where structurally these two graphs are different. So here our conclusion is the two graphs are not isomorphic, or structurally they are different graphs. Now, what happens if we still really wanted to look at these two graphs, but we want to get at least the potential for them to be isomorphic? And so to do that, I added in one extra edge for the first graph right here. So for this first graph, we still have the 6 vertices, but now we have the extra edge. I went ahead and highlighted it there in orange. Now we have 6 edges. And we still have the exact same graph H in the over here on the side, so it still has 6 vertices and 6 edges. Now here we also want to check to see if these two graphs are isomorphic to each other, if they are structurally the same graph. Notice in terms of the placement of that extra orange edge in graph G prime, this does now give us what? Structurally, it gives us a length 3 cycle over here, which is good news because in graph G, we structurally had a length 3 cycle as well. So certain components in these two graphs are structurally the same. Now, one of the things, or one of the tricks that people use to check isomorphisms as a first glance thing, is they look inside of the graph and they say, all right, well, let me see what the degrees are of all these different vertices. That way I can start looking at where the edges are living. Because remember, in the isomorphism, you not only are mapping your vertices to each other across the two graphs, you also have to preserve where your edges live. Okay? So if we look at the vertices in graph G prime, notice this top vertex has degree 1. This second vertex has degree 1. Third vertex has degree 1. The vertex in the middle here looks like it has degree 5. And the two vertices on the ends of the new line segment both have degree 2. Okay? So structurally, this tells you that that middle vertex has to connect to all of the other vertices in the graph. And then you've got some other stuff going on too. Now, if we then look at the graph H and we look at the same thing, I'm going to start over here on the side. So if we look at this little triangle type shape, we see that this top rightmost vertex has degree 2. The vertex under it also has degree 2. Good news. We have degree 2 here also on that length 3 cycle. Then we come down here, and on these two vertices, they're both degree 1. Good news, we have some degree 1 vertices over here. And then we have our last two vertices. Notice here, this one is degree 3 and also degree 3. Now that right there is problematic for us because notice these guys with degree 3, we don't have any vertices that are degree 3 over in that graph G prime. So notice what those degrees are actually allowing you to see. They're telling you that, hey, yes, we do have one of these length 3 cycles in both graphs, but over here in graph H, it's connected on this vertex that's sort of up at the top. But over here in graph G prime, this cycle is connected right here, sort of in the middle of this same, let me actually highlight it here for us. Make it maybe, I don't know, how about orange. This piece right here that kind of looks like a line and an extra line coming out. A line and an extra line coming out. Notice in terms of where that length 3 cycle is connecting, it is connecting at structurally a different part of that orange highlighted subgraph. Okay? What that means is those degrees changed from the two highlighted degrees of 1 and 5 to the two highlighted degrees of 3 and 3. So that interior structural change is actually highlighted when you look at the degrees. With the degrees not matching, there is some sort of structural difference. So this tells us that even though we bumped up the number of edges in graph G to get graph G prime, we still don't have a graph that is isomorphic to H, because even though there's the same number of vertices and edges, structurally there's something different in the middle of that graph. Okay? But that right there is a crash course in terms of isomorphic graphs, as well as what an isomorphism is. Definitely there is more to all of this stuff, but that would be a first glance.